When you attach a chart to an LLM chat and ask what changed here, the interface makes it feel simple. There is an image, there is a question, and a few seconds later there is an answer. But inside the model, the chart cannot just be handed over as a picture. A language model does not naturally operate on pixels the way we do. It works with context, pieces of information arranged in a form the model can process. So the first mystery is this: how does this image become context? That is the thread we are going to follow. Not can the model see in the human sense, but something more mechanical: what has to happen to this chart before the LLM can use it to answer a text question. With text, we already have a familiar route. The sentence is broken into tokens. Those tokens become embeddings. Then the model processes them as part of its context. The exact tokens are not always whole words. A tokenizer might split a word into pieces, keep punctuation separately, or represent common fragments directly. But the important idea is simple. Text already has a path into the language model. The chart does not. The chart starts as a grid of pixels. A blue line is not automatically latency. A red marker is not automatically deployment. A spike is not automatically an event. For this video, we will use a few public openly described architectures as reference points: YT for patches, CLIP for image text alignment, and LLaVA, which we will call LLaVA, for a clean vision to LLM bridge. These are not the only possible designs, and private systems may differ, but they give us concrete mechanisms we can inspect. Before we cut the image into patches, notice something important about the chart itself. The meaning is not in one pixel. It is not even in one line segment. The meaning comes from relationships. The spike matters because it happens after the deploy marker. The recovery matters because it comes after the spike. The axis matters because it tells us whether the change is large or small. The title and labels matter because they tell us what this line even represents. So the visual pathway is not just trying to remember the image. It has to preserve enough structure that these relationships survive the translation. If the deploy marker disappears, the model might see a spike but miss the context. If the axis becomes unreadable, it might describe a trend but get the scale wrong. So now the question becomes sharper. How do we turn the chart into pieces while still keeping location and structure? A simple way to start is to divide the image into patches. In a YT-style vision transformer path, a patch is often a small square crop from the image. The YT paper's key move was to treat an image more like a sequence, split it into fixed-size patches, embed each patch, add position information, and let a transformer process the sequence. That does not mean every modern model uses this exact recipe unchanged, but it gives us the core intuition. Each patch contains raw pixel values. On its own, a patch might be boring, a bit of background, part of a line, part of an axis, maybe a fragment of text. The model projects that patch into a visual embedding, a learned vector representing the visual information in that region. A text embedding starts from tokenizer output, a visual embedding starts from pixels inside an image region. And because the same crop can mean different things in different places, the patch also needs position. At this point, the image is no longer just an image. It has become a sequence of visual embeddings, where each patch embedding carries visual information plus position information. But those vectors still do not automatically mean the same thing as language. This is where alignment enters. Clip is useful here because it trained image and text models by comparison. In each batch, the model saw images and possible captions and learned which caption matched which image. Matching pairs were pulled closer together in representation space. Wrong pairs were pushed farther apart. The result was that images and text could start sharing a useful map of meaning. For our chart, that means a visual pattern can be represented closer to matching descriptions, such as spike after deploy, than to unrelated descriptions like flat CPU or web page. Clip itself is not a chat model, and this is not the whole multimodal pipeline, but it explains one important step: how visual patterns can become connected to language meaning. Even after alignment, there is still one more problem. Aligned visual features do not automatically fit inside a chat model's context stream. The vision encoder produces vectors in its own format, while the LLM expects embeddings in the format of its text token stream. LLaVA is a useful open example because it makes this bridge easy to see. Its system combines a vision encoder, a learned projection layer, and a language model. In LLaVA, the projector is a lightweight learned projection layer. More generally, these bridges can be small learned neural network modules. The projector is not the main language model, and it is not doing the reasoning by itself. Its job is to map visual feature vectors into the embedding shape the LLM can accept. The conclusion for a mental model is this: the image is not sent into the LLM as raw pixels. It is translated into LLM-compatible embedding tokens. In a LLaVA-style design, those projected image features can sit beside text tokens, so the model can answer using both the question and the visual evidence. Now the original chat finally makes more sense. The user typed a question, and the image pathway translated the chart into evidence the language model can use. The question can now point back into translated chart evidence, the deploy marker, the spike, the pre-spike trend, and the recovery. The answer is generated from that conditioned context, not by reading raw pixels one by one at response time. This is why the visual pathway matters so much. It controls what evidence is available to the language model. If the important relationships survive, the answer can be grounded. If they were compressed away, the answer may still sound fluent, but it has less evidence to stand on. Video uses the same broad idea but with time added. A video is not usually handed to the language model as one giant raw file. Systems sample frames, encode clips, or maintain some kind of visual memory. A sampled frame can be treated like an image. A clip encoder can capture motion across several frames. Either way, the representation needs more than X and Y position. It also needs time. The context stream now receives evidence like this visual feature from this frame or clip at this position around this moment. That is the bridge from video to an LLM. Sampled or encoded visual evidence becomes time-aware context. Once you see the compression path, multimodal mistakes become less mysterious. The model may understand the broad scene while losing fine details. Depending on resolution and pre-processing, tiny labels can blur, exact chart values can be uncertain, and small positional differences can shift. A fluent answer can also add a cause that the image evidence never actually proved. This does not mean the model saw nothing. It means the model saw through a representation. The chart was translated, compressed, aligned, and inserted into context. So the failures become easier to predict. Look for the details most likely to be lost during that translation. Bayezid. The full mental model is a chain of translations, not eyes attached to words. The chart becomes patches. Patches become visual embeddings. Visual embeddings are connected to language meaning. A bridge reshapes them into LLM-compatible embedding tokens. Then the language model generates an answer conditioned on that context. The important thing is not to memorize one architecture. It is to keep the chain in mind. Every step changes the representation, and every step decides what evidence survives. That is the model to keep when a product says it understands images or video. If this helped you build a clearer mental model for multimodal LLMs, please consider subscribing. We will keep breaking down complex AI systems visually, one mechanism at a time.